Hello there. During this session I'm going to be talking about the magnetic forces on charged particles. So a charged particle feels a force when it moves through a magnetic field. Think about what factors might affect the size of this force. Okay, so the factors could be, and I guess this is hopefully you thinking aloud, you'd be thinking, well, it's got to be something to do with the strength of the magnetic field. That's definitely one. The size of the charge would be another one. And a third one, which you may not think about, but makes sense if you consider the impact of current when we're looking at wires in the magnetic field, if we look at the velocity of the charged particle as well. I'm going to explain all that during this session. So let me take you through that. And the diagram I should mention on the left hand side has an electron traveling into a magnetic field, and what we can see is the force on it as it works perpendicular causes it to have a circular motion. In this case it has a helical motion, and what we see here is something which quite commonly happens when we're talking about charges and magnetic fields. Questions are often about the shape that the charged particle follows as it passes through the magnetic field, and I'll give an example of that at the end of this session. One thing I should mention, because I'm going to reference it in a proof, is something called the drift velocity. Now, drift velocity is the average velocity that a particle attains due to an electric field, and this is the erratic motion due to collisions with ions. So if a particle electron is passing through a copper wire, the overall velocity and its motion would be known as the drift velocity. Okay, so I'm just clarifying that because I'm going to use that as I develop some ideas. So first of all, let's redefine current. Okay. We accept that current equals charge passed divided by time. That's acceptable. Now, what I can do here is, rather than thinking of the total charge, I can break this down into the amount of electrons and that pass by. So we're going to call something called the electron density, which is N, and for that I'm going to work out the total volume, so that's area times length times by the density, that gives me the number of electrons, multiplied by the charge of an electron, which is obviously E. So therefore I've reconfigured what Q is. Q equals ALNE. Taking this a little bit further, if I see that we have length divided by time, well, length divided by time is basically a velocity, so therefore I can change that to my drift velocity. So the current now equals nave, the number electron density multiplied by the area multiplied by the drift velocity multiplied by the charge of an electron. Now, I'm going to combine that with Bill. We know that force equals the force on a wire equals the magnetic field strength times the current times the length of the wire. So I'm going to use that, and I'm going to try and now think about the individual electrons. So therefore, I'm going to now replace current, and now I've got NA, and I've switched it to Q just because I want it to be able to fit any charged particle. So I had E previously, and now I'm going to just make it a little more general. I'm going to say Q, which is the charge of the particle, times the drift velocity times length. From here, if I just expand it out, and I've expanded out this in purpose, I'm going to have the charged particle density multiplied by the area multiplied by the length multiplied by the magnetic field strength multiplied by the charge multiplied by the drift velocity. The reason I do that is that NAL is the total number of charged particles. So then the force on each particle becomes F equals QVB. So remember, the density multiplied by the volume is actually just telling me how many particles there are in total, and if I divide my force by that number, it tells me the force on each particular particle. So the force on each particular particle becomes the charge multiplied by the velocity times by the magnetic field strength, which is what I alluded to at the beginning of this session. So when a charged particle is moving at 90 degrees to the force, to the field, the force can be calculated from this factor. Force multiplied by the flux density, multiplied by the charge, multiplied by the velocity of the particle. So F equals BQV. And it's important we recognize this is moving at 90 degrees to the field. If it wasn't exactly 90 degrees to the field, we'd have to take that into consideration, and we'll have a sine theta there. Because obviously sine 90 equals 1, it simplifies for that situation, but otherwise we have a sine theta here. Now, in which direction does the force act? Well, the force is always at 90 degrees due to both the current and the field, and you can again use Fleming's left-hand rule to find out its direction. So now the left-hand rule applies for conventional current. Conventional current is actually the opposite direction which electrons flow. So a negative charge moving to the right has to be treated as a positive charge moving to the left. Okay, that's one thing you have to think about. So the direction the current flips over in the opposite direction. Remember, you must point the middle finger in the opposite direction to the movement of the negative charge. This is the thing that people fall down on, okay? It's the thing I'm going to keep on saying. So think about this carefully. Okay, we've got that. Let's try relating this to circular motion. So now what we have now is if we have a particle moving around in a circle, we know force equals mass times acceleration. And we know that in a circular situation, acceleration is v squared over r. So what we have is, as long as everything's at 90 degrees to the field, qvb equals mv squared r. Okay. And what you can do is you can work out the force going into the middle of the circle. You can use that using Fleming's left-hand rule. So we think now we have a positive charge moving. Here we have, so that means that our finger of a current points in the same direction as that positive charge. So our positive is moving around. What we can do is we recognize that the field is, the opposite way. The field is going to be moving out of the paper. We can see that coming out. If we use Fleming's left-hand rule, we realize that the positively charged particle for current-wise is going in the opposite direction, and therefore the field is going, force is going into the center of the circle. It's providing the centripetal force. So just check that with your fingers. Remember, the important thing is to recognize about the flipping which is involved when it comes to the direction that the particle is traveling. Obviously now we can simplify. QB equals mv over r. And therefore the radius of this circle is going to be the mass times the velocity divided by b times q. Let's give this as an example question now. A proton has a mass of 1.67 times 10 to the minus 27 kilograms and a charge of 1.6 times 10 to the minus 19 coulombs. Moves in a circle of radius 21 centimeters perpendicular to a magnetic field of 4,000 Gauss or 0.4 Tesla, which is what we're interested in. Find the period of the motion and the speed of the motion. So take a moment here, put your ideas together, think about circular motion here, think about what we're going to have to find out. Okay. And let me take you through this now. We know that QVB equals mv squared over r. Therefore, we can rearrange this to show that V equals BQR divided by M, which comes out at 8.05 times 10 to the 6 meters per second. T is the period, so we've got 2 pi r divided by V, and that gives me 1.64 times 10 to the minus 7 seconds.